foundational skills? What are the opportunities in the professional world for you? And I'm assuming that is a topic of interest for most of you. So let's get started giving a little bit of background about myself. For about 4 years ago, I published a book which is related to the architecture of industrial IoT. So industrial internet is a terminology that General Electric, where I used to work at that time, uses for the industrial segment of IoT. And we will, as we go along, we will tell you what are the different segments of IoT, and we'll give some examples to help you understand what does IoT mean in the real world scenario. Then a few months ago, we published another book. Mahesh is one of the co-authors. That's titled Industrial Digital Transformation. So one way I look at it is, a few years ago, my book was about building IoT capabilities. And then this book, the more recent book, is about using those foundational capabilities, IoT, AI, and cloud computing, other things, to deliver business value, whether it is to companies, consumers, governments, public sector. So this recent book focuses a lot about using all those technologies and delivering value to make real use of the technology. So this recent book, we had a total of 4 authors. Each of us have worked in the industry for at least 25 years. So we had a lot of industry background, which helped us write the book in about 6 months last year. So it's very recent content. As you can see, Mahesh, and then one of the other co-authors, and is now the CIO of Department of Energy of US Department of Energy. She has a deep public sector background. And then Nital was my undergraduate colleague from IIT Kanpur. He did his PhD and has been working with Intel ever since. So interestingly, we had 2 people with semiconductor background. So Mahesh will use some examples of how silicon is an important part of IoT solution. So in terms of the agenda, we'll introduce what's IoT, what are the career options around IoT, okay, whether you can take a hardware-centric path, Mahesh will focus on that, or how AI is an important part of it, or you can take a software-centric path around IoT. Both those options are possible. So I'm assuming this session should help you that as you go to your undergrad college and you have to look for what majors to focus on, you can get some idea of understanding of what could be a potential target profession for you and what kind of foundational skills you can develop in your college career. And of course, you can get started on some of those things right now as you are in high school. And I think Meher is a great example where he's ahead of most high school students in terms of building the foundational capabilities. And then we'll look at how all that applies in industrial settings. Why is it important to apply IoT in industrial settings? And then how, at large, companies are deriving value from all these foundational capabilities. So we'll show you real world examples where IoT is in use, it's delivering value, even though it's a fairly recent trend, like last 5 years or so, we have been talking about IoT a lot more. So now let's go into some examples of what is IoT, and let's define that in terms of few examples. So we all know that computers were connected through internet, right? That started maybe 25 years ago, started well before I'm assuming many of you were born, where computers, servers, things like laptops, phones were connected to each other. That was the internet, the classic internet. But in last 5 to 10 years, we have started seeing that physical devices, which historically had no computers in it or had no connectivity to it have started connecting to the internet. And that is the origin of sort of Internet of Things. And to do that, these things or physical devices now may have sensors, may have software, may have connectivity technology like the radio. And Mahesh's company builds a lot of these components, so he has first-hand knowledge of all these things. So all of a sudden, cars and homes and refrigerators all of a sudden are now having computer-like characteristics, because that's what is needed to connect it to the internet to make this Internet of Things. So as we go along, I want to give a sort of high-level positioning. Many of us are familiar with the traditional IT, right? Most of you probably already know that if you want to take a career in IT and computer software development and so on, that what kind of path you will take, right? And in real world settings, that organization is often led by either the chief information officer, CIO, in traditional companies and end user companies who are consumers of technology, or if it is a software building company, then you may have CTOs or product leaders or development leaders, software engineering leaders who lead those kind of organizations. And that is the traditional world of information technology, where typically software is written on computers and deployed on computers and helps to run the business. Now there is whole another section which is known as operational technology. So this is still the technology, but that's used to run the factories, to run manufacturing processes, to run supply chain and other things, to keep the physical world going. So if you are planning to become an industrial engineer, or there is a lot of use of technology where, let's say in a factory, industrial equipment is connected to each other, like an assembly line. They are historically connected to each other, but isolated, because historically there was no need for an assembly line to connect to internet. So all the technology that keeps factories and distribution centers, warehouses, and other things going, those are generally called operational technology. And in last 5 years or so, we have seen that the two have started coming together, and that's where we start talking about IoT systems, which if applied to industrial settings is called industrial IoT system. So there is whole new profession has developed, which kind of takes skills from both the branches and combines it and tries to build systems and applications to deliver value. So when we talk of IoT, you will typically hear, again, it's fairly subjective, but you will typically hear 2 or 3 main branches. One is consumer IoT, and one is either commercial or industrial IoT. The major difference between the two is we as individuals are consumers of technology. So as homeowners, we may use a Nest thermostat, which is a very simple example of a connected air conditioning system or thermostat to the internet. Fitbit. As humans, we can be treated as things, where if we put on a wearable device like a Fitbit, measurements about us can be taken and shared in a connected system. Or a recent example is home gym equipment, because people were confined to home in last year or so. Peloton and Nordic Track and others have come up with connected home gym equipment, which have added a lot of value, and we'll see some examples of that. So these are examples of consumer-centric IoT, where the business is using IoT technology to deliver value directly to a consumer. Now, when we look at commercial or industrial segments of IoT, then commercial IoT examples can be fleets. So if you own a fleet of cars, or UPS delivery vehicles or industrial other kinds of specialized vehicles, then that's a fleet of vehicles, and you may track the location or condition of that fleet through connected cars and vehicles. Your buildings could be connected. Nest is an example of home connected, but commercial buildings could be connected because air conditioning, heating, and cooling is a big part of running the building. It's a big cost. And if you can optimize those things, and if you prevent breakdown of air conditioning and other things unexpectedly, then that's a value IoT can deliver in the commercial space. And again, there are communities. When we talk of cities, communities, things that are often in the public sector, those can also benefit from IoT. For instance, in recent times, not every home had broadband internet, and kids had to do their homework. So cities started making the parks as hotspots or other communities as hotspots so that kids could continue their education seamlessly, because not every kid was lucky enough to get a hotspot from their school district. So there are various ways to add value through connectivity in community settings, public sector, and so on. And given my background from General Electric, I'll also use few specific examples from industrial IoT, such as factories, power generation or electricity, and so on. And these are big problems to solve. If you solve it once, let's say you improve power generation, in theory, you could scale it very easily to other power generators. And a company like GE, which produces a third of world's electricity, if they solve that, if they improve power generation, then in theory, a third of the world's electricity generation can be improved. So these are big bets that companies have made in last few years. So now let me show you when you want to look, whether it's from a career perspective or out of curiosity, as to what are the companies who are really enablers of industrial IoT or consuming industrial IoT. And you might see some familiar names like Microsoft and Amazon AWS or IBM or Oracle. These are names you are familiar with. Whenever we talk technology, we talk about these companies. So that's obvious. But you'll also see a lot of names you may not even have heard of. PTC. And by the way, this is the way that you read this is the higher the positioning along this axis, that means they are visionaries and their ability to execute is high. So the leaders typically tend to fall along these lines. So these are kind of the leading companies in this space. These are the trailing companies in this space, but they all are worthy of mention by an important industry analyst called Gartner, who creates this, what they call a magic quadrant. So why I'm sharing this with you, you can see some companies so that you know that maybe while you are in college, you're looking for internship and you're interested in this IoT space, then you can see what are the companies you may aspire to get internship, to get first-hand knowledge of this area. And PTC is one of the leaders. You may have heard of Hitachi as a maker of computers and industrial equipment, but they are also one of the leaders in IoT. So is General Electric or GE Digital, where I used to work. So you will see on one hand, there are software companies who are featured like Microsoft. On the other hand, companies which used to make or still make physical equipment like Hitachi, like Siemens. Siemens doesn't make it here, but Siemens is also a player. Or Samsung. Samsung makes phones and electronics. GE makes industrial equipment. Why are all these companies which had nothing to do with software technology all of a sudden showing up here? Because these companies realized that they make critical equipment which are used in the industry. GE makes engines for planes. 70% of the world's commercial aircrafts run on GE's engines. So these companies realize that, hey, we know how to make physical things, and now we can improve them by software. If we do it ourselves, if we build our software capability, we already understand how things work. If we marry the two together, we can really make some good software-driven, IoT-driven solutions. And that is why Siemens, Hitachi, GE, all these are important players in this space. So now let's look at why is industrial equipment a prime candidate for industrial IoT. So let's start at the bottom. I'm sure most of you are familiar with smartphones. An iPhone might cost $1,000, but typically it lasts 2 to 3 years, or it becomes sort of obsolete at that point. Cars maybe cost $30,000, or a used car might cost $5,000, and they last maybe 10 years. So compared to the age and value, the industrial equipments, they last much longer. An aircraft can cost $150 million. The engines might cost $20 million, and they last a long time, even up to 20 years. So, or trains or power generation and so on. Or even in a building, the AC system lasts 15 years or so. So these are high value problems to solve through IoT. If we can make a difference in reliability of an aircraft, or how the HVAC system is operating, so the energy costs, which are a big part of operating cost of a building, especially a commercial building, we can get large benefits out of it. And that's the reason there is a lot of investment, interest, and potential benefit by investing in IoT solutions for industrial equipment. So now let's look at how do we go about it. Okay, so you're all familiar with, I'm sure, like Android as a platform, or the iOS as a platform. So if you have to build an app, you choose a platform, because if you build it for iOS or Android, then you know that a lot of basic things you don't have to worry about. And even for users, most people have one of the two smartphones. They can very easily use it on their machine. So it helps to accelerate the development process, and it helps to standardize it. Likewise, because there is a lot of interest in IoT and realization that IoT can solve a lot of high value problems, there is a increased focus in last few years about building an IoT platform which has the general which meets the general requirements of IoT problems, like connecting devices, running, doing something with the data, something useful with the data, and then delivering it in form of application to the user, the outcomes of that. So what are the typical characteristics of an IoT platform? It should allow connecting the devices, right, which are often referred to as endpoints. These are the actual physical equipment. And then ability to capture events of interest, or as we call it, data. Now, the data may be captured right when it's happening. For instance, when you have a Fitbit, your heartbeat or your steps are captured. Some things may be captured right away, transmitted to cloud. Some things may be stored and later transmitted, or some things like temperature of the room. You don't need to measure temperature of the room every 10 seconds. Every 15 minutes might be sufficient. Every hour might be sufficient. So in general, an ability to connect and collect data at a reasonable frequency, that's one key capability. Then we talked about different manufacturers, right? You can have a home HVAC system from Carrier, from Trane, different companies. Now, they may have internally used different technologies. So even to read the temperature value from one system versus other, you may have to deal with different ways of interpreting the data from the sensor. So that's where protocols and other things come into picture. And a IoT platform with its edge counterpart, and we'll look into what is edge, has to take care of ability to read the data of interest from a native format, ability to convert it into a format that can be easily stored in a computer system in an IoT platform. Likewise, ability to analyze the data. Some data has to be analyzed right at the edge. So take the Fitbit example. If your heart rate goes, let's say 160 degree, the 160 frequency or rate, then the Fitbit should right away alert you that you are probably in danger zone or you need to slow down. It cannot rely on the cloud to go and fetch that, hey, 160 is not good. It should be able to make that decision right on the edge. But from a historical perspective, that, hey, are you often exceeding 150 or whatever a reasonable value is, it may store that information in the cloud. So all those are capabilities of a complete IoT platform in combination with cloud and edge part. Likewise, it has to, an IoT system cannot operate in isolation. It has to work with the IT systems of the company, which are the more mature technologies. And then it has to allow building applications on top of it, just like iOS lets you build an application or an app, iPhone app of interest. So now let's look at a very high-level architecture of IoT platform. So IoT platforms typically have the platform tier, or what is known as the core. This may often reside in public cloud like Amazon or Azure. And then it has the edge component. Edge component facilitates the connectivity of the physical device to the platform. The platform may reside in cloud or in data center, but the devices, physical devices like an aircraft may be sitting on a runway or in an airport, or a factory may need to be connected. So those are typically things that are often outside of the parent company who's trying to connect them, like the trucks may be on the road. So you need a whole edge tier to have a standardized way of connecting the devices, which may or may not have a native way. For instance, your old refrigerator doesn't have a way to connect directly to internet. Maybe the new smart device or smart refrigerator may have ways, but likewise, your old factories may not have a inbuilt connectivity to internet. So this edge tier of the IoT platform, in combination with edge gateway and other devices, helps to connect the physical world to the IoT platform. And then the IoT platform allows building business applications in combination with IT systems to deliver value to the business users or end users. So now let's look at an example of how industrial analytics work. And what is analytics in this context? So you all know about artificial intelligence or machine learning. And the general term of those is either AI or analytics. Okay, so analytics helps to get value or understanding from the data. So far we talked about the need for connecting devices or things to the internet and how we connect to them, how we gather the data in a platform. Now, what do we do with the data? So back to Fitbit example, the Fitbit may be recording our steps, our heartbeat, but we have to know what use is that information, right? You have to know how many steps should you target per day, and so on. Or just the trend that, hey, am I walking as much as I used to, or am I running as much as I used to? So those trends are analytics. How much you should, what should be your target? Those are the general problems of analytics and AI. So how does it work in a business setting? You have business users, subject matter experts who knows what things to improve. Then you have data scientists, people who have math and stats background, who are good at AI and ML. Often they are PhDs or masters or computer science graduates who have come relatively newly to the workforce. So they understand the mathematical techniques. They know how to write AI models. So somebody might say, okay, I know how to clean data, because when you collect data from devices, there may be impurities in the data. For instance, the temperature sensor might sometimes misbehave. I should be able to identify outliers. So you can write a model for that. Or how to correlate heartbeat with health of a person. You can write a AI model for that. And data scientists generally can write those individual models from a mathematical perspective. And then you can take a number of those analytics, let's say cleaning the data, then applying a pre-processing, or then making a decision that, hey, based on this scenario, I need to apply this analytic, but if my data is of the other type, I need to take another decision, and then combining the results. So these are chain of analytics or machine learning models, which can be brought together to solve a complex problem. And then this is just the analytics part of it. The whole platform, IoT platform, deploying the IoT platform, all that takes typical software engineering skills, maybe cloud computing and general ability to incorporate machine learning into a broader software process, and then deploying it, whether it's for your own company, whether it's for your customer's company, so that the business users can see what was the outcome of the machine learning model, and the analysts can provide feedback and improve this process. So this is a general process, applies to any AI learning, but as well as to industrial settings. But generally, the problems are quite complex. So you may need a combination of machine learning models chained together, or as we call it, orchestrated together. So now I will give you a real world example, which is an airlines engine, how IoT can be used for solving a real world problem, which is a high value problem. And what is that problem? As we know, aircrafts are expensive. Engines are a critical part of an aircraft, just like an engine is a critical part of a car. Health of an engine is extremely important because you don't want any engine problems when the aircraft is midair. Likewise, if you can make the engine working properly, then it may not it may reduce the fuel consumption, and fuel is a big operating cost for the airlines. So these are high value problems worth investing, both from an airline perspective or the manufacturer of an aircraft or the engine. Since I used to work in General Electric, which makes majority of the aircraft engines, I have familiarity with this area, and I'll use that example, how an IoT problem is applied to this. So now let's look at what is on the screen. When you all know, when we sit in an aircraft, it is in a stationary condition, the engines are off when we board the aircraft, and then the engine turns on, it taxis on the runway, and at some point it takes off, right? So there's a steep upward movement when it takes off, and that is the part where the engines are put under extreme stress because it is lifting hundreds of people. Imagine the weight of an aircraft off the ground into the air. Then it keeps climbing for, let's say, 10-15 minutes. Then it reaches a cruising altitude, maybe 30,000 feet or something close to that. Once it reaches the cruising altitude, that's when it's the least stress on the engine, because at that point it's almost like floating in the air, and engine has to do very little work just to keep it at that level. And then descent is the least stressful part from an engine perspective. Of course, it requires a lot of skills on part of the pilot. So now let's correlate that. If the aircraft and the engine were a connected thing, then how we would collect the data, interpret it, and make decisions based on that. So two things we'll look at is how can we use the information collected to predict when is the right time to service the engine so that engine doesn't fail, engine doesn't misbehave, and airline can plan where the aircraft is, where the engine is for servicing it, because aircrafts fly to different locations and each airline has hub locations or main locations where they have more presence, where they have their staff and crew like aircraft engineers. They don't want to be caught off guard where an engine is at a small airport where they don't have big presence and it requires services. And we also want the engine to be operating in such a way that it is consuming least fuel, because fuel efficiency is very important as well. So now let's go to the next and let's focus on the right hand side. So this is a cross section of an actual aircraft engine, and every commercial aircraft has either 2 or 4 such engines. And again, that's for safety, that if one engine fails, there is at least one engine which can help to carry out or safely land the aircraft, or 4 engines typically seen in cross-continent kind of aircrafts, which are much broader, and they have 4 engines, 2 on each side. What does an aircraft engine do? We burn fuel, and the burning of the fuel helps to move the turbine, which sucks in air, and that flow of air, as it goes past the aircraft wings, generates a lift, because the angle of the wings is such that when air is coming horizontally, the tilt of the wings helps to generate an upward lift. And of course, the pilot can reduce the lift when they are landing. So now let's look at how to make sense of this. Okay, so what we are plotting here is, over the duration of the flight, the temperature of the gas coming out of the engine. That is a reflection of the temperature inside the engine, the operating temperature of the engine. And we are burning fuel, so the temperature is going to be fairly high. Okay, so let's interpret this. When the engine is stationary, before engine is switched on, it's the ambient temperature or the environmental temperature, whatever the outside temperature is on a normal day. And then as it switches on and starts to taxi, the engine temperature keeps rising. And then we talked about the takeoff part, which is the most stress on the engine, because it's now lifting off the ground at a high speed. The takeoff, and that's where the engine is stressed the most and the temperature rises the most. So in this case, the temperature rises to about, let's say, 750 degrees. And we all know from the material sciences or mechanical engineering that when materials are subjected to very high temperature, and in this case, aircraft maybe flies twice a day or a couple of times a day, when material is subjected to high temperature, heating and cooling, sudden heating and cooling, that over time it loses its characteristics. That means material corrodes, a metal or alloys, they corrode if they are subjected to heating and cooling. So that's a domain knowledge that you have to know. A product engineer, a manufacturing engineer of the engine has to provide that kind of knowledge to a data scientist who's writing the analytics. The data scientist understands the data, which is the temperature, how it is changing, how to plot the data, how to write machine learning models purely from a data perspective. But that's where the domain knowledge helps us interpret the data and make sense of the data. So in this case, temperature rises as it is taking off, and then it is continuing to climb. During takeoff, it reaches the highest point because it is stressed, and then at some point, as the climb continues, it's not as steep as the takeoff. the engine slightly gets a slight relief because it's not working as hard as takeoff during the climb. And then as the climb continues, it is still high temperature, but it's stabilizing based on how much is the climb. But as you can see, takeoff is the extreme, then the climb, and then the cruise is where it stabilizes. And the aircraft spend, if it's a long distance flight, aircraft spends the most time in cruise, right? The takeoff might be 10, 15 minutes. And then let's say you're flying from New York to Los Angeles, a 5-6 hour flight. You may spend in cruise most of the time, okay? And that's where they are optimized for. So this is a good example where we apply industrial IoT or machine learning for a industrial product, and how we capture data through an IoT platform and provide the basic building blocks to build applications on top of that. The application may now look at the whole history of the aircraft over last 1 year, 6 months, and decide if it has been exposed to extremes very often. Now it needs inspection. Now it's not safe to operate it. When to have a downtime on the engine, take it off the engine, send it to factory for replacement of parts which are subject to failure, and so on. Okay. So let's move along, and I will quickly hand it over to Mahesh. But let me just set one context that, hey, now we have talked about all the enabling technologies, and at the end of the day, business users are interested in deriving value. So an airline may be interested in extending the life of the engine, reducing the maintenance cost, reducing the fuel cost. So for achieving all that, you not only need technology components, but you also need a lot of changes in the business and ability to adopt. There are cultural changes needed. So all that is needed together to achieve business value. Now, let me quickly give you some more examples in recent times that you may be familiar with. A Peloton bike, a home gym equipment. Through connected equipment, Peloton has been able to get a big market share and drive sales and pretty much revolutionize the home gym industry. They saw opportunity, they had the product, they connected it, were able to deliver good experience. Likewise, Lululemon, a company which still makes athletic gear, bought a company called Mirror, another example of a connected consumer device, a mirror, where an instructor can see you, the mirror can give you feedback, again, a connected exercise equipment. So these are simple examples, not as complex as aircraft example, to understand where connected products can deliver a lot of value through IoT. And of course, these are augmented by typical IT solutions like mobile app and so on. This is a tablet app. So you do need the traditional IT skills of building apps and so on, but they are all enhanced by a connected product in this case. There was a news that Joe Biden uses Peloton, and apparently every morning he and his wife decides who gets to ride the bike first. So a good example of a company who has capitalized on a connected product to capture market share. And another example which I showed you, Lululemon acquired this company Mirror to get that kind of capability, because Lululemon used to make yoga pants and other things, but they were quickly able to jump into this opportunity and buy a sort of IoT capability. Okay, so with that, let me hand it over to Mahesh. And Mahesh, okay. I can run the slides for you.
Sure. Okay. So, I work in semiconductor industry. I work for ST Microelectronics. It's one of the leading players that builds microcontrollers, builds various sensors, which are used in, a large variety of applications. Starting from automobiles to your mobile phones to your Fitbit-like devices to defense and aerospace. and many other in agriculture, smart city, all of that. So I'll talk about two aspects. One is AI and machine learning, and the second is how this all is being utilized in various industries and various industrial applications. Various when I say industry, it does not mean heavy industry like a oil refinery or a steel mill. I also would use that term for consumer electronics, which you can imagine is the industry that brings you mobile phones and smart devices. Alexa at home falls under that category as well. So with that, Sham, next slide, please. Yeah. So a brief history about AI and machine learning. So we have heard this term AI, and we think that this is a recent phenomena, but in reality, research began on this topic in 1940s and 50s. And that's where scientists started thinking about artificial brain. And the term artificial intelligence was actually coined by John McCarthy in 1955. And the real research work started out of a workshop that was held at Dartmouth in 1956. And there are various famous papers that came out of that workshop that are considered as foundational in the space of artificial intelligence. Then you would say, what happened? So at that time, the compute part, which is necessary for artificial intelligence, was just up and coming. Computers were not as advanced as what we have today. Until invention of transistors and development of personal computers, you really could not do much in the space of artificial intelligence in those days. Next slide, please. So here, I also want to use this time to talk about three different terms that we hear when it comes to AI. So one is artificial intelligence, then you hear the term machine learning, and then the third one that you would hear is deep learning. So what exactly is the difference? So this particular slide shows you this. So artificial intelligence is a superset of studies where machines would mimic cognitive human capabilities. So the definition from Tom Mitchell, essentially is this. I'll just read it off the slide. A computer program is said to learn from experience E with respect to some class of tasks T and performance measure R if its performance of tasks in T as measured by a performance measure P and improves with experience E, which means the machine is learning with experiences, and you have a performance measure, you have certain tasks, all of these different aspects define machine learning. So what is deep learning? So deep learning is again another subset of machine learning. So in case of deep learning, you would hear the term artificial neural networks. So artificial neural networks essentially derive the architecture and the model based on functioning of human brain. Next slide, please. So I want to now jump into the discussion as to why really do we need machine learning. So as you can imagine, there are certain problems that can be solved if you can mathematically write a formula for it, or you can derive the mathematical model for a particular problem. And there are many examples. Many problems have been solved like that. Some classic examples. Consider the cruise control in your car. The problem in this case is you want to maintain the speed of the car to a set value. So you can have a model around it that if the error, meaning if the difference between the speed of the car to the given speed of the car at any given point of time is positive or negative, then you apply gas or you apply brakes, and that's how you can maintain the speed of the car. So there is a simple mathematical model that can be put around it. But now think of the problem where you are trying to do handwriting recognition, handwritten digits. Now, what exactly is the mathematical model can you develop around recognizing whether the number two that you see written as number two is recognized by the machine as number two? It's a really, really complex. You cannot write mathematical models for this very easily. So that's where you need machine learning. And machine learning, as I'll talk in a few other slides, learns from the data, that you provide. Next slide, please. So machine learning is actually a process. And in this process, there are two different parts. One is the training, and the second one is the inference part. So for training, if you were to teach a machine how to recognize digits like numbers 1 through 10, then you would collect lots of data, which means you would have hundreds of people writing numbers 1 through 10. Each person would write it differently. But then you would teach the machine that all the number ones that have been written can be labeled as number ones, and number two, number three, number four, and number 10, and so forth. And you feed this to the machine learning algorithm. So it could be an optical system that looks at these images, and then from that it derives this knowledge. It takes in the labeled data and starts to build a machine learning model. And the next step is you test it. How well does your model work? So in this case, you would take a different set of data than what was used as the training data, which means you will have the person whose data was not used in the training, you would ask them to write numbers 1 through 10, have the machine learning algorithms do the detection. So does it recognize 1 as 1 and 10 as 10, or 2 as 2 and not 3? So essentially that is your validation. So once you complete the validation, then the model is ready for deployment, which means then you can deploy this in a system which is going to read numbers 1 through 10. So this simplistic example that I talked about can be extended for many, many applications, whether it is for self-driving cars to robots controlling different tasks in a factory. Next slide, please. So the process I briefly described is collect data. You have to clean the data, because a lot of times data has spurious information, extraneous information in this. And as Shyam had mentioned, there are experts who essentially extract important features from that data. So this is the second stage. Then you train the model, you test the model, and fine-tune the model based on your testing, and finally deploy it. So that's the machine learning process in 5 steps, 5 quick steps. Next slide, please. So very, very briefly, there are a large number of machine learning algorithms that are available. And there are classical machine learning algorithms, to reinforcement machine learning algorithms, to neural networks and deep learning algorithms, and to ensembles. So ensembles and each of these set of algorithms are applied in different scenarios. Next slide, please. So here, I also want to, you would hear these terms. So I'm just very quickly going through this. You would hear supervised learning and unsupervised learning. So what does that mean? So the very first example that I use for machine learning, where you use training with labeled data, that is supervised learning. In cases where you do not have such labeling information available, which means you're constantly feeding all the data, and from that you're deriving the models, that's called as unsupervised learning. And there is something in between called as semi-supervised learning. And then there is a fourth one called as reinforcement learning, where you learn as you go, and you deploy an algorithm and you learn as you go. And there are a large variety of these algorithms. Wikipedia has quite a lot of information on it, which you can find on your own when you have time. Next slide, please. So machine learning, the most important part for this thing is data, lots and lots of data. So high quality usable data will result in high quality models, and thereby very good performance of machine learning algorithms. Next slide, please. So as you can imagine, if you have large amount of data that have been collected from all of these IoT nodes that Shyam talked about, whether they are on your airplanes, on an airplane, you can have a large number of sensors that are collecting data and you're sending this data. Now, in order to process this data, you need large servers. So you would essentially get this data to your large servers, essentially in the cloud environment, and that's where you would do your computations. You would do your archiving of the data, which means you have history of the training of the models that has been recorded. Results from previous computations have been recorded, and different models that you have played with have been all recorded. And the new data as it comes in, you decide to use it based on what you have learned from the past. Next slide, please. So sometimes, data cannot reach the cloud, and there are, 4 different reasons. One is physical reason, the second is economical, the third is privacy, and the fourth one is power. So battery-operated devices, for example, if you go to the next slide, please. Yeah, battery-operated devices, they have a power restriction. So which means you cannot use a lot of power to keep sending the data to the cloud. In some cases, physical requirements, which means like, if there's health data, then you do not want to send this to the cloud. Privacy reasons, is another example where this is, and economical, it might not, bandwidth, cost money, to transfer data, you need to utilize certain amount of bandwidth. So if that is not economical, you would not send the data. So where is this all leading to? So that's next slide, please. That's where, machine learning, on the edge comes in, which means, devices, let's say you have an aircraft, spacecraft rather, you need to run machine learning algorithms on this spacecraft. It has no connectivity, it has no reasonable connectivity to reach, servers on the Earth. So what would you do? And that would be your machine learning at the edge. Another example is, many solutions that require instant reaction. Shyam used the example of somebody having a heart attack and your Fitbit device, instantly determining that the person is having a heart attack. So that is an application driven by latency. And, all the computations and all the model and inference from these models, model computations and inferences from those models are all done on the device itself. So that's machine learning on the edge. Same thing for industrial applications, like, robots out there in the factory, where they have to do complex tasks at a very high rate repeatedly. They also apply machine learning on the edge. Next slide, please. So, the main idea is, you would have latency and communication cost restrictions that require local processing. You would have network bandwidth issues. And wherever connectivity drop is not acceptable or tolerable for user experience, that's where you would use, machine learning or AI on the edge. And data privacy reasons, where the data cannot leave. Let's say a company is working on sensitive data for their processes, and the data cannot leave the machine and cannot be put onto the cloud. So that's where, you would essentially have AI on the edge. Next slide, please. So, if you think of edge, there are, 3 different areas that, you would see being 3 different terms that you would see being used. One is, of course, computations in the cloud that we talked about. Then computations on the edge that we talked about. In this case, it could be on your phone or your laptop or, your Fitbit kind of device. And the third one is deep edge, which means the computation is done now within the sensor itself. Because remember, sensors are sensing your real world environment. The example that Shyam used for an aircraft, it's the temperature sensor in the airplane engine that is sensing the real world, the temperature. Next slide, please. So now, what is happening is you are moving all of these computations, whatever you can, on the edge to meet various objectives that we talked about, the various constraints that we talked about. Next slide, please. So this is where, you would start to see these solutions for AI get implemented everywhere. And this is in your robots that you would have, or smart buildings for applications such as energy saving. You have HVAC systems, or you have lightings in these smart buildings that should be, smart lighting essentially would give you the needed illumination at the right time, those kind of things. Smart cars, self-driven cars with autonomous driving, personal healthcare devices, smart farming, smart homes. That's, you will have sensing everywhere. And these sensors are beginning to become more and more intelligent, where you are embedding intelligence in the sensors themselves. So smart industry has predictive maintenance kind of applications, where the machine can tell you how much of a useful life is left before the next maintenance should be done on this. Rather than just changing the oil of your car every 5,000 miles. If the car were to tell you that no, oil in the car is fine, we can go for 9,000 miles as opposed to 7,000 miles or 5,000 miles. That's your smart predictive maintenance. So next slide, please. So you would see IoT and MEMS everywhere. You already see them. Shyam gave examples of this, and this particular slide has quite a few more. So whether it is in your home or in your industry or agriculture or many other applications. So
Mahesh, you want to describe what is MEMS? They may not know.
Okay, MEMS stands for micro electromechanical systems. So these are tiny sensors. You would find your sensors in these. Take the example of your iPhone or your phone, mobile phone. When you rotate your phone, your screen orientation changes. That's driven by a MEMS accelerometer. So I want to leave a few minutes for questions for Shyam and I. So I stop here.
All right, thank you so much. I think if anyone has questions, they can just make sure to ask in like either the chat or the Q&A, and then we'll be sure to like see if they can answer it. I think there's a bit of a delay on the slide in the presentation. So once this questions, if there are questions, they should be coming into the chat soon if there are any.
Yeah, Mayor, if you have any question, you can ask in the meantime.
From my end, I'm just sort of taking in a lot of the information that you're talking about. Like,
Yeah.
I guess
any feedback from did that cover what you think would have been useful? Anything in future we should have added or changed?
I think it was really, really great. Like you talked about everything from like the beginnings, like the basics of like what is IoT, all the way to like what actually like the applications of it in like industry. You talked about consumers, you talked about different companies, and then moved into AI. And I thought it was something that a lot of people I know like are interested in things like that in sort of AI or an IoT. So it's really good for them to like learn how, and really good for me too to like see if it's something I'm interested in the future. I think one question just came up in the chat. It says, have IoT developers found a way to safeguard the edge tier software from cyber attacks?
Yeah, so I can try and answer this. There are more and more such capabilities that are being added to guard against this. So smart sensors, if you just take that example, the logic that runs inside the sensor, it is guarded by protective mechanisms on the gateway, because gateway is the way you would reach the sensors. Before you even reach the gateway, again, you have solutions that are being added at various entry points, if you would consider those. So speaking from edge and gateway perspective, yes, this is already happening.
Yeah, and I'll give another extreme example, nuclear plants. Now, some of them are also connected, and obviously that's a very risky proposition. So there are ways to safeguard when critical infrastructure like aircraft and nuclear power plants or even generators are connected. Often it is only to read the data. The system only allows reading and collecting the data, and then the IoT platform makes decisions, and there is a human in the loop to implement that outcome. So when should an aircraft engine be serviced, or does it need inspection right away after this flight? That information is passed on to a human in the loop, and there is no direct information allowed to be sent to the engine, let's say to shut down the engine. So these safeguards are built in critical systems where either unidirectional information flow is allowed, or it can inspect what kind of information is being sent and block those commands.
There was another question: how to merge IoT and local technology. This is again, fusing of physical world with the models that live in your machine learning, the machine learning algorithms. And as an example, those models, this is where you would see solutions being implemented on the edge. And just take the example of smart agriculture. To determine, which parts of the field, should get what kind of fertilizer and how much of the fertilizer. So this information is available now from remote sensing satellites that essentially can give you the information from past several years of data, and you can determine, which areas, how much planting needs to be done, which areas need to be have, what kind of fertilizer, and what kind of crops. Moisture, humidity, all of that information in real time, temperature, all of that, information that is available to you even for smart agriculture. So it is now merging of these two. You can see agriculture being, one activity, and IoT, is helping improve this, and helping get a lot more visibility into what's actually happening.
I think one more question I just got sent was, if you were like looking into going into like IoT and AI, like the combination is like, what should they like concentrate in as like an undergrad student, or when they're moving on from high school, like what can they do sort of like projects wise, or when they're moving into undergrad and moving into college, like what should they concentrate on if they want to go into like a career in IoT or in like IoT and AI, the combination?
Yeah, so maybe I'll answer part of it. One of the slides we had was this. These are the companies, at least as of today, according to Gartner, are the leaders in either building the IoT technology for industrial use, or they are also consumers, like GE and Hitachi are also consumers of the technology themselves. So if you are looking for internships, try to explore with these companies if you are interested in industrial IoT. Or the other route is AI. As you saw, AI applies. I mean, Facebook uses AI, Google uses AI, as well as industrial companies use AI. So if you want to keep your options open, we told you what are the enabling technologies, cloud computing, and ability to build scalable platforms which can handle data and analytics. All these are very generic skills. If you build those in your undergrad or through internships and others, you could branch off in any direction, a traditional IT path or an IoT path. But at some point, if you are more interested, then explore. Just go and check what kind of jobs these companies are advertising for. Search with IoT in the job search, or what kind of internships, or explore internships in these companies, and that will put you on the path.
You would need the foundation of statistics, of mathematics. Essentially, if you have a computer science, electrical engineering background, mechanical engineering background, it really enables you to solve many of these very interesting problems in this space.
Okay, thank you so much. One more in the chat.
Yeah, so are there any IoT developments? What I keep an eye on is look at every large technology company has their annual conference. And luckily last year, a lot of it was digital, like content is freely available for review. So Amazon as a company has their event reInvent. If you look at the content of reInvent, you will see what are the things they have released cloud companies are now implementing or developing devices which you can use in your, let's say, in your factory to act as a gateway device, which can quickly connect, just like is it called the Echo Dot or the device Amazon gives you where you press it to reorder something. So that sits in your home, lets you easily order something from Amazon.com. Likewise, companies are building these connectivity devices which you can pretty much very easily add to your factory to be able to connect to, let's say, IoT cloud. Or Microsoft is building IoT and digital twin software, which are all in this space of IoT. So the traditional cloud computing companies are releasing a lot of new capabilities in form of features in their IoT platform and making it easy to bring it to the edge.
Okay. Let me see. I'm trying to see if there's any more questions that come up. But if there aren't any more questions, then I just want to say thank you so much again for coming here and like taking the time to do the presentation. And like I got a lot out of it, and I know like a lot of the people in like the audience, like they definitely got a lot out of it too. And it was like it's a great way to like learn a lot of information and sort of experience a lot of IoT, because like I know if you try learning on your own, it's a lot harder to like get all this information at once. But thank you so much for being here and like helping us out with like this presentation and everything.
Yeah, I think this slide, yeah, my contact information is here as well if you want to reach us. Thank you.
Thank you. Bye-bye.
Bye.